Hi. My name is Adisorn from Postec Pre-Stressing Thailand. Welcome to my presentation. Today's topic is Design Optimization of Post-Tension Slab with Slab Band, using Simulated Annealing Algorithm. This presentation will show an example of using Simulated Annealing Algorithm and Optimization Design of Post-Tension Slab. The objective of this study is to show the potential of using modern optimization technique in automated design process. This might be interesting as a future trend in engineering design. Why optimization? The main purpose of optimization is to make things better. We normally do optimization in our daily design routine. This might start with 1. Initial guess of slab thickness including slab band and drop panel. 2. Check for punching shear strength of the slab. 3. Compute the amount of tendon required. 4. Adjust tendon profile and check if all design constraints are satisfied. If the design is not satisfactory, then repeat step 1 again and again. This sounds like tedious work ahead. The concept of computerized optimization is widely used in the design of post-tension slab through computer software. In our development of PTO-PTI module, the optimization is automated as the following process. 1. Setup problem and constraints. 2. Let the optimizer determine what the best solution is. 3. The designer can adjust the given solution if needed. The optimization process is done through simulated annealing algorithm. In common post-tension slab design practice, it is sometimes a judicious decision to use slab band whenever slab is not thick enough to accommodate the required tendon sag. This is especially when the span is longer than 10 meter or when heavy loads are occupied. Not only slab band can cut down the amount of tendons used by allowing tendon drape at larger value, but it also eliminates the cost of punching shear reinforcement at column support. In this example, I will show the design of 4-span continuous PT slab. The design objective is to minimize overall construction cost. The design variables are slab thickness, projected depth of slab band or stem, number of strands, and tendon drape. The design dead load is 3 kN per square meter, and live load is 2 kN per square meter. The objective is to minimize cost of the construction. Next, the design constraints or the design requirements are as following. 1. Allowable flexural stresses according to ASEM21 82011. 2. The requirement that the number of tendons for interior spans must be less than that of exterior spans. 3. Average precompression is between 1 and 2 MPa. 4. Percentage of balance load is controlled in range of 70 to 150% of slab self-weight. 5. Geometric control of tendon profile or drape. 6. Deflection limit is controlled under L/800. 7. Flexural strength, and 8. Slab band assignment criteria. Let's dive into simulated annealing process. Simulated annealing is a member of the so-called metaheuristic search algorithm. Those kinds of search use stochastic or random process as part of finding optimal solution. It should be noted that, while some metaheuristic searches employ multiple agent-like particle swarm optimization, simulated annealing algorithm uses only a single search agent. So the programming part is much more simple but trade-off by slower performance. In any metaheuristic search including simulated annealing, two main differences from the traditional gradient-based optimization algorithms are as follows. 1. We don't need to compute any gradients of the objective function, as they are not used in the calculation process. The searching process is random by nature. 2. For each iteration, worse solutions are also accepted for the next round of continuous search, under a specified tolerance. With this concept, it allows the process to move over traps from the local minima toward global minimum. Since simulated annealing is a single-agent search method, it can only get a single solution at a time. This solution can be either better or worse than the current one, which can be explained as follows. First, use a random walk to explore the solution at an early stage. Next, use probabilistic condition to exploit the better solution. This means non-improvement solution might be accepted as a candidate as long as it is satisfied the probability condition. The key parameter to control the acceptance of a worse solution is so-called the cooling temperature. During the process, the cooling temperature is continuously decreased in order to scope for a better solution. The lower the control temperature is, the harder the worse solution will be accepted. From this example, it is shown that when lowering the cooling temperature, the solution is converging to the global minimum. The animations show the solution process on MATLAB. The initial temperature is set to 1.0 and then reduced for each iteration. It can be seen that the solution is converging while the cost function is finally minimized. This table compares the optimal solution between post-tension flat plate and post-tension slab band system. It is obviously seen that when including slab band as another design variable, it is possible to get a better design solution, in other words, the cheaper design. Thank you for your kind attention. I hope you find our presentation is useful. See you soon. Goodbye.